remember at the end of the last video I said just shove in the number. So the real name for that is the direct substitution property. And what it says here is if I have a function that's a polynomial or a rational function, and I'm talking about a limit at a point that's in the domain, then I can just shove in the number, okay? The important point here is this little bit where it says A is in the domain. So this goes back to our very first example where we talked last week about limits. So let me write that down and we'll see what's going on. So we looked at this from the perspective of geometry. We drew this and we just described the graph and figured out what was going on at the point x equals 1. And you can still do that, but now we can do it algebraically. But look what happens if we try to just shove in the number. Okay, I put in 1 here. Obviously, I've got 0 in the top, but I also have 1 minus 4 plus 3, so I've got 0 in the bottom. So this is 0 over 0. Now, 0 over 0, and we've discussed this 0 over 0 thing a number of times in these videos, right? What this is, it is called an indeterminate form. If I've got 0 over 0, I don't know what that is. It doesn't mean it's 0. It doesn't mean it's infinity. It doesn't mean it's 7. It means I need to do more work. So if you ever get, when you get 0 over 0, means do more work. It means you're not done yet. Because that expression doesn't mean anything yet. But you can make it mean something. It means you're not done, but you can finish. So specifically, and for this one we know what we need to do because we did it already, right? You just go ahead, but what the point is, the point that I'm trying to make before I go ahead and do the problem, the point is that I know I need to do this precisely because when I went to try to use this, it says, oh, if that was a polynomial or rational number. When I tried to do this, I got something that alerts me to the fact that, oh, something wrong here. You're not done yet. And it alerts me to the fact that, yeah, in fact, this number 1, that's why that fails, the number 1 is, in fact, not in the domain, right? Because when I do this, and when I factor it, which is the first thing I want to do in the problem, so I factor it, minus, right? Now I factor it and I see something that I can cross out, or I can cancel. The x minus 1's cancel, right? It's okay to cancel it because this is the limit. We're taking the limit as x goes to 1. We're not at 1. We're going there. So it's okay to cancel it because I'm talking about the limit. Those two, we're not at the point 1 yet. So now I rewrite my thing everywhere except the point 1. This is perfectly fine. And since we're not at the point 1, it's perfectly fine. And now all I need to do, now I'm okay. Because my new form here, right, is a function which has no problems at 1. All I need to do is stuff in the 1. So I get my answer. Which, if you remember, is the right answer, right? Because that's where that little hole was. Okay? You won't always have to do this. Let's say it asked me for the limit as x goes to 4 of this function. And I think we actually did look at that before, but I'm not 100% sure. It doesn't really matter. Now if I go ahead and stuff in the number, I'm going to have 16 minus 16 plus 3. So I get 3 over 3 and 1. So here I didn't have to do any simplification precisely because I didn't have 0 over 0. Right? I had some other point. The point 4 is perfectly happy in this domain of this function. Okay? So the only points, if you remember, that were questionable were 1 and 3. And so, yeah, if I was taking it to 3, I would end up with a 0 in the denominator and a number in the top, and I would end up with infinity. We will talk about that. We won't talk about that in this section. So in this section, you should be getting a finite number. Okay, so let me do another example. Actually, let me do a very simple example, but that sort of illustrates what we were talking about in this last part, where we divided out the x minus 1, because although you're taking the limit near 1, you're not actually at 1, right? So a very simple example that helps us show that is some nice, I'm still at 1. Sure, I'll do this one. I'll do some other things that are some other numbers in a minute, but why not? Okay, so this is another example where basically the same thing is happening. So visually, 1, 2, 3, 1, 2. That's not the right slope. That's better. And at 1, I've got 2 pi, which is like 6.28. So we're going to put that somewhere up there. Okay. So we know from our discussion that actually the limit here should be the it should be the y value, which is 1. So how do we do this problem algebraically? Well, what do I stuff in for f of x is the question. When I'm writing this down, we're getting precisely the point that I'm taking x to 1, but I'm not at 1 yet. So I'm going on this line from this side, or I'm going on this and I'm going on this line from the other side. I'm approaching 1, I'm not there yet. Therefore, I use the part of the definition, because we have this piecewise definition, but I want to use the part of the definition that goes with where I am when I'm taking my limit, which is that I'm not at 1. So you just put that in there. And now it's very easy to just put in the 1 for x. You don't even have to write that as a separate formula. You could have gone directly to 1 because that's easy. You could do that in your head. But if you want to write it, that's fine. I wanted to point out one more thing. Then I'm going to stop this video and do another one with some... Oh, no, I want to do one more example before I stop this video. Also, not that complicated an example. So let me do that, and I'll talk about my one more thing while I'm doing that last example. It's pretty similar to the first example, so it's good enough to have it in here. But yeah, I'll do some example where the point is not 1. 2x squared plus 9x minus 5, and then x squared minus 25. Okay, I've got negative f5 here, so this is going to be 0 in the bottom. I already know that. I want to check what I've got in the top. I'm going to have 2 times 25 minus 45 minus 5. So this is indeed that form 0 over 0, which means we need to do some more work. Okay? So if I work, when I've got a bunch of polynomials like this, I want to factor them, right? And one of the things I wanted to point out about these examples, you will notice that I'm writing this limit every time. And it does seem to be a pain to do that, but you need to do that. Like, you need to write the limit every time. You don't have to do it, like, you don't have to do writing the limit in here or stuff the way I did that first crazy example, which was not crazy, but it was just very long. But just keep the limit out here and make sure you write it in each step until you actually evaluate the limit by plugging in the number. So that's an important thing, that you keep that there so that you know what you're doing, and so that I know, at what point you actually plugged in your numbers for real and evaluated the limits. So let's see, this is going to be 2x and x, and I've got 5 and 1. Okay, so I want to do 5 times 2. So that's going to be this, 5 and 1, but it's going to be plus, so this is plus, and that's minus. Okay, so I have factored my top. And now I can see, again, -5. I know I did it right? Because the 5's cancel out, the x minus 5's cancel out. Now I no longer have something that turns out to be 0 over 0. I have something that I can plug in the number, because -5 is fine here. I'm not getting 0 in the denominator. -5 is definitely in the domain. So I just plug in my number. As I said, then once I plug in the number, I don't have to write the limit business anymore. So what is this? This is -11 over -10. So we can just write 11/10 there. Those minuses cancel out. Okay. So in the next video, there will be more complicated examples.